Hi everyone, this is Wei. I'm from University of California, Riverside. The topic of this presentation is partial discharge detection with convolutional neural networks. In this presentation, I will first introduce the background and motivation of this work, and briefly summarize the existing literatures. In the second place, I will describe the overall problem and the proposed technical methods. The numerical results and the conclusion will be presented at last. The power line faults that result in sparks and ignite nearby tree branches contribute to the increasing number of wildfires in the United States. As we know, it has been confirmed that the deadly wildfire of California in 2018 is caused by power line fault, which results in billions of dollars damage and losses. To reduce the number of potential power outages and wildfires, the utility companies are enhancing vegetation management. However, it is very labor-intensive and costly. For example, PG&E have invested about $1.6 billion during 2030 to 2070 to conduct vegetation management. An alternative solution to mitigate power line cost ignitions is to replace existing belt conductors with cover conductors. However, when vegetation comes in contact with cover conductors or conductors slapped together, partial discharge could occur in deteriorated insulation systems. The partial discharge is a small electrical spark that occurs across the surface of insulating materials. It happens when the electrical field exceeds the breakdown strength of the insulation material. The partial discharge could first degrade the insulation system and eventually lead to power line faults and wildfires. Therefore, it's crucial to detect partial discharge. The partial discharge detection problem has been extensively studied in the existing literatures from many different aspects. The first group of papers provides a detailed description for the mechanism and the phenomenon of partial discharge, not only in power cables but also in capacitors, transformers, and rotating machines. Comprehensive measurement and experience for partial discharge events are performed with various sensors. In the second group of papers, the partial discharge detection is treated as a classification problem. Different methods such as statistical learning, signal processing algorithm, support vector machine, and artificial neural networks are proposed to solve the problem. The deep neural networks are also applied in recent years as in the third group of papers. The 1D convolutional neural network is adopted in paper 5, while in paper 6, a long short-term memory model is used to classify different categories of partial discharge signals in power electronics devices. However, most of partial discharge detection methods are developed and evaluated based on high-quality signal measured in laboratorial environment. The last group of papers start to investigate partial discharge detection with real-world noisy measurement from high-frequency voltage sensors. It achieves the state-of-the-art performance in the field deployment by selecting input features based on domain knowledge and adopting random forest algorithm. In this paper, the partial discharge detection is treated as a binary classification problem, while the same open dataset available online is used. The dataset contains voltage measurement from inductors installed on three-phase power lines of an electrical grid operating at 50 Hz. The voltage measurements are collected from all three phases at the same time. Each single-phase voltage signal samples contains 800,000 measurements over 20 milliseconds, which covers a full operating cycle. The voltage measurements are scaled into integers within range negative 127 to 128. There are three major technical challenges in detecting partial discharge based on noisy and high-frequency real-world voltage measurement and label data. The first challenge is that the voltage measurement contains a significant amount of background noise from several sources, including radio emission, power electronic devices, lighting, switching operation, and corona. Secondly, dimensionality of the voltage signal is significantly larger than the sample size, while only 6% of the voltage signals have partial discharge events. Moreover, the information regarding the start and the end times of partial discharge events in the time series are not available. In general, it's extremely difficult to identify the subsequence associated with partial discharges in each row voltage time series. The proposed technical approach contains three main components, which are signal preprocessing, converting 1D signal to 2D images, and adopting convolutional neural networks. In the signal preprocessing stage, we first take two denoising steps to remove the normal frequency component of the voltage data and the high frequency background noise. The 50 Hz component of the voltage signal is always present in a voltage waveform, which does not provide any useful information for the partial discharge detecting problem. To remove it, we first normalize the original voltage signal with integer data points into range of -1 to 1 and then pass it through a discrete time high-pass filter. To remove the high-frequency background noise in the voltage time series without diminishing the voltage spikes of interest, apply the discrete wavelet transform. In practice, the discrete wavelet transform can be implemented by passing the discrete signal through a cascaded filter bank. Each time, the signal can be decomposed into approximation component and detail component. The high-frequency background noise can be suppressed by truncating the detail coefficients. The bottom figure shows an example that the base waveform and the high-frequency noise of a raw signal is removed successfully. To reduce the dimensionality of the voltage time series, we perform the max pooling, which maintains the positive spikes. The partial discharge could occur in any subsequence of the preprocessed 1D voltage time series. Thus, it's more appropriate to extract information from each of the subsequences in the preprocessed voltage time series. This can be achieved by short-term Fourier transformation, which has been widely applied in sound recognition and enhancement. The discrete short-term Fourier transformation first divides the whole time series into subsequences with overlap. Then the discrete Fourier transformation is performed with the multiplication of the window function and the signal function over each subsequence. The bottom image shows an example of what a log spectrum looks like after the transformation. In the last stage, we adopt two state-of-the-art CNNs, which are VGGNet and ResNet, to solve the image classification problem. The architecture of the two CNNs are shown in the figure. Both networks are constructed with basic building blocks. The basic building blocks of VGGNet consists of stacked convolutional layers and a maximum pooling layer, while the maximum pooling layer is used to gradually reduce the feature dimensionality. The ResNet introduces a bypassing route from the input to the output in the basic building block. By hypersizing that, it's easier to optimize the residual mapping. The fully connected hidden layers with ReLU activation are used right after the building blocks. For binary classification problem, the output layer is a single neuron with sigmoid activation function. To mitigate the unbalanced issue, the balanced sampling is adopted for network training. To further reduce the variance of the model outputs, a bag of ResNet and VGGNet are trained and ensembled with average voting. In the numerical study, our proposed method is benchmarked with the empirical feature extraction-based approaches, while the expert-selected statistics of the peaks are used features, which include the mean value, max value, and the max ratio between consecutive peaks. The random forest gradient boost tree and the recent proposed bidirectional LSTM with attention mechanism are used as classifiers in the benchmark. The Mathieu correlation coefficient is adopted to better evaluate the model performance on unbalanced dataset. The outputs of all the algorithms are in range 0 to 1. The final binary label is obtained by comparing the outputs with the threshold. A bag of models are trained by repeating the 5-fold cross-validation multiple times with different random seeds. The threshold that achieves the best MCC score on the validation data using the average voting results is selected as the optimal threshold. The MCC scores for the two convolutional neural networks with average voting over the training, validation, and the testing data are shown as follows. As shown in the table, as ResNet optimizes over residuals, it's more likely to be affected by spikes and the non-Gaussian noise from a small dataset. The test MCC score drops significantly with about 11% when the noise filtering is removed. However, the noise filtering step could remove some useful information in the raw data. This is why the noise filtering caused the performance of VGGNet to deteriorate by 2%. The comparison of the benchmark algorithms and the proposed method is shown in the following table. The accuracy score of all methods are very similar because the majority of the samples is without partial discharge. The MCC is better performance metric for unbalanced dataset. It can be seen that the two convolutional neural network-based methods achieve better performance. By blending the two CNNs and introducing diversity in the network structure, the final MCC score is notably improved by more than 5% compared to the gradient boost tree model. To further interpret the convolutional neural networks, the occlusion experiment is conducted. At each step, a small portion of the image is occluded with a mask. Then the same classifier makes a prediction based on the new image. At last, the occlusion map is obtained by stitching together the prediction results from shifting the mask across the whole image. As shown in the bottom subplot, the predict class value has a significant dip when the mask is placed around 4.5 and 12.5 milliseconds, with frequency range from 2000 Hz to 4000 Hz. The corresponding time intervals in the original time series could be identified as potential voltage signatures for partial discharge events. In conclusion, an innovative machine learning algorithm is proposed to detect partial discharges of covered conductors. The powerful convolutional neural networks are leveraged by transforming the 1D voltage signal to 2D spectrum. A noise filtering step can improve the learning efficiency and accuracy of ResNet. An occlusion map of convolutional neural networks is constructed to help identify suspicious time intervals when partial discharge occurs. The evaluation results show that our proposed algorithm achieved notably improved MCC scores. That's all. Thank you.